Hi guys. Okay, so today we're going to take the idea that we started formulating in class, clarify it, and then expand on it. So we're going to start with the mean value theorem. So we were looking in class today at several graphs, and we came up with the mean value theorem. Now remember what we decided was that if f is continuous on the closed interval, so it's important that it's continuous on a closed interval, okay, and differentiable on the open interval from a to b, so that's an open interval, it does not have to be differentiable at the endpoints, then there exists at least one number c between a and b such that the derivative of f at c equals f of b minus f of a all over b minus a. Now, yes, this f of b minus f of a over b minus a is the slope of the secant line. Remember, that's also the average rate of change. Now, not only is that true, but this f prime of c, that's an instantaneous rate of change, and not only that, it's also the slope of the tangent line to the graph. And that's what we were looking at in class today. We were looking where the slope of the secant line was the same as the slope of the tangent lines. Now, and so graphically, we looked at the mean value theorem. Now we're going to look analytically that means the derivative of the function f at c is equal to the average rate of change of f over the interval from a to b. Okay, so that's the mean value theorem in a nutshell. Now there's a physical interpretation. So we've looked analytically, we started graphically. Let's look physically for a minute, like a real life application here. A trucker handed in a ticket at a toll booth, like you're getting on the thruway, showing that in 2 hours, he covered 159 miles on a toll road with a speed limit of 65 miles per hour. So if you get on the New York thruway and you get a ticket at the toll booth, and then you drive, and then as you get off, you hand in your ticket, and it shows you've driven 159 miles in 2 hours. He was giving a speeding ticket. Why? Well, his average velocity would be the 159 miles divided by the 2 hours he drove, and that gives him an average velocity of 78 miles per hour. And by the mean value theorem, okay, there has to be a time when his instantaneous velocity was 78 miles per hour. Since the average rate of change, or the slope of the secant, was 78 miles per hour, at some point during those 2 hours, he was driving 78 miles per hour. So he gets a speeding ticket. Now let's take a look at one totally analytically. So here we have the function f of x is x cubed minus 7x plus 6, and we want to find the number c that satisfies the conclusion of the mean value theorem for f on the closed interval. Now, first of all, before you can use the mean value theorem, you have to remember f of x is a polynomial, which is wonderful. F of x is a polynomial. We love polynomials. Okay, because that means f of x is continuous and differentiable everywhere. F of x is continuous on that closed interval from 1 to 3 and differentiable on the open interval from 1 to 3. So the mean value theorem applies. You have to know that it applies before you can use it. So now we know that our mean value theorem says f prime of c equals f of b minus f of a all over b minus a. So I need to find my derivative here. F prime of x is, the derivative of x cubed is 3x squared, minus the derivative of 7x is 7, and the derivative of 6 is 0. So f prime of c then would be 3c squared minus 7 equals, now we need to find f of b, which would be f of 3 minus f of a is 1 over 3 minus 1. So we still have 3c squared minus 7. Now f of 3, remember here, I'm going to write f of x down here, x cubed minus 7x plus 6. So f of 3 is 3 cubed minus 7 times 3 plus 6. 3 cubed is 27. 7 times 3 is 21. So 27 minus 21 is 6 plus 6. That's 12. F of 1 is 1 cubed, which is 1. Minus 7 times 1 is 7 plus 6. So 1 plus 6 is 7. Minus 7 is 0. Over 3 minus 1 is 2. So 3c squared minus 7. 12 minus 0 is 12. Divided by 2 is 6. Now we need to solve for c. So we're going to add. Then we're going to divide by 3. Now when we take the square root, we get two answers, the positive and negative square root of 13/3. But remember, c has to be in that interval between 1 and 3. So c is only the positive square root of 13/3. That is the one number where the derivative is the same as the average rate of change. There you go. So again, just to remind you about the graphical interpretation, mean value theorem says there's at least one point C in the open interval from A to B where the tangent line to the graph of f is parallel. Remember, parallel means same slope to the segment with endpoints here, and that's the secant line. Okay, and here's a picture to remind you that the slope of this secant is the same as the slope of this tangent and is also the same as the slope of this tangent. So in this particular case, we have two values where this works. Okay? Now comes Rolle's theorem. Now Rolle's theorem is a corollary to the mean value theorem. A corollary is a theorem that comes directly from another theorem. So it's a special case of a theorem, but it's a theorem in and of itself. So Rolle's theorem says, suppose that y equals f of x is continuous on the closed interval from A to B and differentiable on the open interval from A to B. So far familiar, right? Just like the mean value theorem. But now there's an extra condition. The extra condition says that if f of A equals f of B equals 0, so your f of A is here on the x-axis, f of B is on the x-axis, they both have a height of 0, then there exists at least one number c, right, just like in the mean value theorem, between A and B, at which this time the derivative has to be 0. And the reason that is because this graph has to either go up and then come back down to 0, so it has to have a maximum, or it has to go down and then come back up, so it would have to have a minimum. So if the function values are both 0, there has to be a turning point somewhere, which means there's a horizontal tangent line. Okay? Now there's a variation on Rolle's theorem which says, starts out the same way, okay? That we have, it's continuous at every point on a closed interval, differentiable in the open interval, but this time it just says that f of A equals f of B. And you know why that is? Because I could take my axes, here's my y-axis, but if I shift my x-axis up here, and now my A and B are, say, -10, I still have the same situation. If you slide the graph translated horizontally up or down, you still have the same thing. If the function is returning to the height that it started at, it has to have a turning point. And if there's that turning point, it's a critical point where there is a horizontal tangent. Okay? All right. Now, we're going to use this variation of Rolle's theorem. Find and mark the values of c where the derivative equals 0 on the following graphs, if applicable. If it's not applicable, explain why not. Now, here's my graph in A. Okay. Does Rolle's theorem apply? No, it does not. Why does it not apply? Because right here at 0, there's no derivative. The derivative at 0 does not exist. It's not differentiable on the open interval. Okay? So f is not differentiable on the open interval from A to B. Let's look at the next one. So here we have a polynomial. That's good. That means it's continuous on the closed, it's differentiable on the open. So here we have, here's our A and our B, there's our secant line. Notice it's horizontal. And yes, I'm going to have a horizontal tangent here and here. So there are two places where we would have a C, right at a max and at a min. Awesome. Now let's take a look at C. So let's take a look. Now I noticed this secant line here, right? And I do see that I have maxes and mins. However, the theorem does not apply. Our function is not differentiable on the open interval from A to B. Right here, there's a cusp, okay? That's what we call a cusp, and it's not differentiable though. Even though you see there are some C's there that work. It doesn't matter, the theorem doesn't apply. All right, last one here. My function is continuous. Is my function differentiable? Yes, it is. But does Rolle's theorem apply? No, it doesn't apply. Does not apply since f of A is not equal to f of B. Now, the mean value theorem would apply, and we could find places where the tangent line is parallel to the secant line. That would work, but we cannot find a place where the derivative is 0. Okay, guys, that's it for today. We're going to work more in class on the mean value theorem and Rolle's theorem. Have a great night, guys. Bye.